Now, prior to jumping into looking at binomial theorem, what we need to do is make ourselves aware of a special type of function that is going to come into play, and that's called the factorial function. Now, this function here looks at products of numbers up to a certain point and how we can apply them to different scenarios, looking at permutations and combinations dependent upon what the question's asking us. Now, the easiest way to think about this is to actually look at an example or two. Let's imagine we're watching a race with 6 cyclists taking part. Now, all 6 of the cyclists finish at different times, so there's no draws, and there's a prize for first and second place. So what we ask ourselves is, how many different ways can the 6 cyclists finish? That's the first thing we need to answer. And then the second one is, how many different ways can the prizes be awarded to the racers? So if we think about the first part of the question, how many different ways can the 6 cyclists finish? Well, there's going to be 6 places, so first to 6th, because obviously there's 6 racers. If all 6 are taking part, there's going to be 6 ways that they could finish first. There's going to be 6 cyclists who could finish first. There's going to be 6 ways. We know there's then going to be 5 cyclists left to finish second, so there's going to be 5 ways they can finish. We then know there's 4 left to finish third, and we can continue on like that, so we know there's then 3 left to finish fourth, 2 to finish fifth, and 1 poor lonesome boy at the end to finish 6th. So in order to figure out the total number of ways, what we can do is take the product of all of these numbers together, and what we end up getting is 720. So that tells me that with 6 cyclists in one race, there's actually 720 different ways or different combinations of people and ways that we can get them to finish. So that's quite a lot of ways. The second part, how many different ways can the prizes be awarded? Well, we know there's a prize only for first and only for second, which means that we focus on this first part here, because what we can do is look at how many different ways they can finish in first, and then how many different ways after that they finish in second. So how many different ways can the prizes be awarded is done by 6 times 5, so there's 30 different ways that the prizes can be awarded. Now, one thing to look at is this part here, so the part from part A, the 6 times 5 times 4 times 3 times 2 times 1. Now that appears in mathematics often enough for us to be able to give it a special name and represent it somehow. And that's doing this. N factorial. N is whatever number we're doing the product up to, and the factorial tells us that we're going to do the product of every single number from that one all the way down to 1. So this calculation here could be represented by the special function 6 factorial, which would equal 720, because that just tells me I'm doing 6 times 5 times 4 times 3 times 2 times 1, and gets that. Now, most calculators, particularly scientific ones that you should be using at this stage, have a special button for supporting that, and they actually have a button for being able to do that. Now, if you look at part B in question 1, we said that there were 30 possible ways the 2 prizes could be awarded because it was 6 times 5. So 6 ways of finishing first, 5 ways of finishing second. Well, if you think in terms of factorials, that can be written as 6 factorial over 4 factorial. 6 factorial, 6 times 5 times 4 times 3 times 2 times 1. The bottom, which is in the 4 factorial, is given by the 4 times 3 times 2 times 1. Now, if you look at these and think of basic calculations involving fractions, these sections here could actually cancel, which would give us the 6 times 5 we would be after. So that there is the equivalent of 6 factorial over 4 factorial. Now this again could then be written as a special function, and that's given by this. So npr, which is equal to n factorial over n minus r factorial. Now in this function, the n and the r obviously relate to certain parts of it. The n is the total number of participants, or the total number of objects that can be arranged. The r is the total number of outcomes that we want. So for the original one, we would want 6p2, because we've got 6 racers and we've got a first and a second place, so we've got 2 possible outcomes or 2 possible ways we want it to be. So this would be 6p2, which is equal to 6 factorial over bracket 6 minus 2 factorial, which then gives me my 6 factorial over 4 factorial. So that would be given by this. Now this function here is often referred to the function giving us permutations or arrangements within a calculation. So it calculates the number of ways of arranging R objects when they're first to be selected from a pool of n objects. So the number of ways of arranging a set number of objects from a bigger picture of objects. So in this case, the number of ways of arranging first and second place from the 6 cyclists. So this one looks at the permutation and arrangements within that. This also allows me to start thinking about a second special type of function as well. But again, easiest way to think about it is to look at it in real application in a scenario. Let's imagine we've got a palette of 7 colours and we want to pick 4 colours to blend. We want to ask ourselves, how many ways can this be done? Now in real life, the order of blending doesn't matter. So we could blend red, blue, green and yellow, and that would give us the same result as blue, yellow, red and green all put together. So there's 4 here that we can stick together, but there's 4 possible ways of arranging them. So we could arrange them as a first, a second, a third and a fourth colour. So a 4, 3 times 2 times 1. Yeah, so there'd be 4 colours we could put in first, 3 we could put in second, 2 we could put in third, and 1 we could put in last, which is the equivalent of 4 factorial, which is equal to 24. Now, if the order of colours mattered, this would be something that would come into play. However, because it doesn't, we don't need to worry about the order of the permutations or the arrangement of them. So what that means is we're actually going to end up with a factor of 24 times the number that we want. So we're going to end up taking 24 multiples into account of the way we can arrange it, because we would then consider the way that we have to arrange the colours to be put in. But in this case, it's not something that we want to do. So what we've got to do is, to get the desired answer, we have to take the permutation, which we had before, so in this case 7p4, so our arrangement of 4 colours from 7 in total, but we have to then divide it by this 4 factorial because it's 24 times too big and it doesn't matter on the arrangement. It's not like the cyclist one. It matters who finishes first, second, third, fourth, fifth and sixth there, but because we're mixing colours, you will still get the same result regardless of which order you mix them in. So that doesn't come into play in this one. The arrangement doesn't matter. Because of that, we're able to define ourselves a second new function, which is looking at combinations rather than permutations and arrangement. And this is referred to as this function here. So NCR. Now C refers to the word combination, which means selecting without arrangement. Because we've got to divide by that extra factorial, we can build that into our formula. Now the formula then for this can be written in this variation here. Essentially, it is the same as taking our permutation formula from before, but dividing it by this factor here, so the R factorial, which takes rid of the dependence of the arrangements. So it gets rid of it dependent on that. This special function comes into play when we are looking at binomial expansion. When we're looking at binomial expansion, it's talking about coefficients and numbers, and when we expand brackets and multiply coefficients, it doesn't matter which order we multiply them in, you'll still get the same answer. If we have to multiply 2 and a 3, you'll still get the same answer as multiplying a 3 and a 2. So the order doesn't matter in that, so it's not permutations, it's more combination we're looking at. So this function here comes into play. Now one thing is, because we're going to be using it so much with binomial theorem, it can actually be quite tiresome to write. So what we're going to do is we're going to change the notation and write it in this format here. So the NR bracket, which is the same as our combinations, is given by n factorial over r factorial bracket n minus r factorial. So for example, if I wanted to calculate the 6c3 out, that would be the equivalent of me doing 6c3, which if I put it in the formula, would be 6 factorial over 3 factorial bracket 6 minus 3 factorial. So it would be the equivalent of 6 factorial over 3 factorial times 3 factorial. Now, 6 factorial, 6 times 5 times 4 times 3 times 2 times 1, and 3 factorial is 3 times 2 times 1. So I can actually factorise out the 3 factorial here, and on the top, just do 6 times 5 times 4. I've then got the 3 factorial on the bottom, so 6 times 5 times 4, 6 5s are 30 times 4 is 120. 3 factorial on the bottom, 3 times 2 times 1 is just 6. 120 divided by 6 is just 20. I could then do the same for this one here, so 1, 1. So what I'd then do for that is I'd do 1, C1. So that's the equivalent of 1 factorial over 1 factorial, bracket 1 minus 1 factorial. So that equals 1 over 1, so they can't cancel out. But here's where the trick comes in. I'm then left with a 0 factorial there, because 1 minus 1 is 0, and it's 0 factorial. So what that means is I want this to work. So at this point here, because of that, what we have to do, and what we're able to do, is define the fact that 0 factorial equals 1. For this to make sense, we have to divide by 1, so 0 factorial equals 1, because of this rule here. This rule here is called Hobson's choice. It can be built in thinking about horses in a race. If there's only one horse, how many different ways can it finish? A key property we have to know about this function, and we have to be able to utilise, is this here. That n r minus 1 plus nr equals n plus 1 r, using the factorials. Now, to prove this, we expand the left-hand side, modify it about, and we can get the right-hand side. So n over r minus 1 factorial is n factorial over r minus 1 factorial, bracket n, it's then n minus the r minus 1. But if I do minus bracket r minus 1, that becomes minus r plus 1. So I end up getting n minus r plus 1 factorial there on the bottom. I then add on the second one, which still takes our original form of n factorial over r factorial, bracket n minus r factorial. Now, to take the next step, what I have to do is put these over a common denominator. In order to do that, what I have to figure out is what I multiply both of these fractions by in order to get that there. First thing to look at is the r factorial. Well, r minus 1 factorial is just one term away. So if I multiply this r minus 1 by r, I get r factorial. So that fraction on the left I can write as n factorial times r over r, bracket r minus 1 factorial, and then keep the second bracket the same, n minus r plus 1 factorial there. What I then need to do is look at this second fraction here and put it over the same denominator. So essentially I want n factorial on the top with something here to then put it over r factorial, remember r bracket r minus 1 factorial is r factorial, then multiplied by the n minus r plus 1 factorial. Well, if I've got n minus r, all I have to multiply that by is n minus r plus 1 to get the n minus r plus 1 factorial. But then to take that into account, I've got to multiply the top by n minus r plus 1 to cancel that out in the long run. So I've now got my two fractions, they're both over the common denominator, I can combine it together. So I then get n factorial r plus n factorial n minus r plus 1 on the top over r factorial, bracket n minus r plus 1 factorial on the bottom. If I then combine the top and play about with it, multiply at the bracket and get it all together, that top can then be simplified to n factorial, bracket n plus 1, and on the bottom I get r factorial, bracket n minus r plus 1 factorial. So that top line is now the equivalent of n plus 1 factorial, and it's then n plus 1 factorial over r factorial, bracket n minus, bracket r minus 1 factorial. Simplify this bracket here, which is then the equivalent of n plus 1 r. So there we go. I've proven that identity by working it through in a generic term. We have to make sure we remember this property because it's going to come in handy and useful when we start to look at binomial expansions using this function.